Good morning, Nanda. Today on complex analysis, today we discuss connectedness. Connectedness we are discussing today. So in the connectedness in the line segment we are taking here Z1 comma Z2. The line segments taking Z1 comma Z2 is a set of the points. Therefore, Z colon Z is equal to Zj plus T into Z2 minus 2. 2 points that we are taking Z2 minus Z1. That is T 0 less than or equal to T less than or equal to 1 we are taking here, where we are taking Z2 Z1, Z2 Z1, comma Z3 Z2, and also the answer and so on. We are taking here Zn minus 1 and Z dash or line segments. These are line segments. Here we can write this set we can write here Z comma Z1 comma Z2 comma and Zn minus 1 comma Z. So we are writing here Z dash. So we are writing here Z, Z1, Z2, Z3, Z4 and so on, Zn minus 1 Z power dash. This is the definition of the connectedness. And one another definition also we call a set which is polynomially connected for any two polynomials we are taking here. Any point to 2 points. What is the 2 points here? Z comma Z dash we are taking. Otherwise, a polynomial Z comma Z1 comma and so on Zn minus 1 and Z dash or joining them, which is also the values contained into the G is on the values Z, Z1, Z2, Z and so on, Zn, Z1 dash also we can take here. We can do it from theorem here. Any polygonally connected set G. G is connected. So any polygonally connected open set G in C is connected. We have to do here. So suppose that G is disconnected. What is the G is disconnected? It is not a connected set. So G is suppose the proof I am taking here. G is disconnected. Disconnected means a connection is a disconnect. There is no connected set is there. So let we are taking here let G1 comma G2 we are taking here let G1 comma G2 we are taking here two non-empty open sets. The two non-empty open sets we are taking two non-empty. Non-empty means any numbers or alphabets is there. Two non-empty sets, two non-empty open sets we are taking here. Two non-empty open sets. So therefore such that G1 union G2 is equal to G. Why? Because G1 and G2 both are in the G. G1 or G2 or G2 or G3 or G3 or G4 or anyone. So G1, G2 are two non-empty sets. G1 union G2 means that's only G we are taking here. But G1 intersection G2 is not equal to 5. The intersection means that value, this value is not matched, that is 5. So therefore, let Z belongs to G1, Z dash belongs to G2. So first one I am taking Z belongs to G1 and Z dash belongs to G2 I am taking here. So therefore there is a polygonal line we are taking here in this condition. But we are taking in this connection in this point of view. G1 union G2 is equal to G, G1 intersection G2 is equal to not 5. But Z belongs to G1, Z dash belongs to G2. These conditions may be written as earlier I told that Z0, Z1, Z2 and so on, Zn minus 1 and Zn out we are writing here contained in G, where Z0 is equal to Z, where we are taking here, where Z0 is equal to Z and the Zn is equal to Zn dash. So Z0 is equal to Z, Zn dash is equal to let take the least number such that we are taking here. Least number means 0 less than K less than or equal to N. So 0 less than or equal to K less than or equal to N we are taking here. But even the K we are taking here, Zk belongs to G2. Zn, Z0 is equal to Z1, but Zk is equal to, we are taking here, Z0 is equal to least number such that Zk belongs to G2. So it is clear that K not equal to 0, Z belongs to G1. Z1 belongs to G1, we are taking here. So now we can take that the line segment. What is the line segments we are taking here? Zk minus 1, Zk. Why we are taking the line segments from minus to first? k minus 1 to k, which is the disconnected set in the discussion here. But z k minus 1 and zk we are taking here is a connector. Why? Why it is a contradiction? So z k minus 1, zk is connected. But z k minus 1 from the definition given in g2 equal g in that one we are told here. So it is a contradiction. So therefore it is a contradiction there. For k minus 1 to k, so therefore g is connected. So another one lemma we have to learn here. Another one lemma we have to learn here. Let G be an open set. Let G be an open set. Let G1 be the set of points. Let G1 be the set of points Z in G polygonally, Z in G polygonally connected to Z0 in G. So therefore, Z0 in G comma G, G comma G2. So G comma G2 is a set of points. Is a set of points we are taking here. Z in G, Z in G we are taking here. Not polygonally we are taking here. So therefore connected to Z0 in G, to Z0 in G are taking here. Then G1 and G2 are, G1 and G2 are open sets. G2 are open sets. What is meaning of polygonally? The meaning of polygonally. Polygonally. What's the meaning of polygonally? Tell me please anyone. Polygonally. Anyone please? G-O-L-Y, G-O-M-E-L-L-Y. Polygonally. So polygonal means relating two-dimensional shape with sides. Two-dimensional shape with straight sides. A polygon is a closed shape. It's meet it is either endpoint. The meaning of all its sides meet at the endpoints. And the dimensional shape with straight line. Dimensional shape with straight side is not dimensional with the shape with straight slides and ఉంటుంది. So it's a closed shape must be at the point is a polygonal we are telling here. Then another one the proof of we are taking here. Proof let Z belongs to G1. Then the Z belongs to G1 means we can say then we are writing here since G is open. Since G is open. Where exists delta greater than 0, where exists delta greater than 0. So W belongs to G. So therefore W belongs to G whenever we are taking here W minus Z less than delta. W minus Z less than delta. If W minus Z modulus of W minus Z less than delta, so that is a belongs to that we are taking here S belongs to we are taking here S belongs to Z comma W at S comma W. So therefore S belongs to Z comma W. That implies that here S belongs to T. So therefore S belongs to Z comma W. That means so we can write S is equal to Z as in the formula and applying the Z plus T into W minus Z. Z into T, Z plus T minus T into W minus Z. For sometimes T satisfying here 0 less than or equal to T less than or equal to. If 0 less than or equal to T less than or equal to 1, we have taken here. So therefore, modulus, therefore, S minus Z minus P of W minus Z, I am writing the simplification of above one, S minus Z, this is also S minus Z, I am taking the modulus minus T minus Z, T minus A into W minus Z, that is equal to, can write that is S minus Z is for P. W minus Z, we can write here it is less than delta we are taking here, that is S belongs to G, we have to write here. So therefore, in this condition, what we are taking here for Z comma W, we are taking here Z comma W, so less than or equal to G. By definition of G1, this is a polygonal line. So polygonal line, already told you polygonal, what is a polygonal? So I told you what is a polygonal here. Again I'm telling you polygonal. It's the closure shape or side means at their points here. So therefore, this Z comma W subset of G, by definition of G1, this is a polygonal line. Already we know that what is a polygonal line here. So what is a polygonal line? Z0, Z1, and Z2, Z3, Z4, Zn, and Zn minus 1, and Z also you are taking here. Therefore, subset of G. So now the polygonal line, the line is called Z0, Z1, Z2, so on Z minus 1, and the Z comma W also is a polygonal line we are taking. W also taking is a polygonal line we are taking here. So therefore it is contained in G. So all the values of G, Z values is there in the G. Again, by the definition of G1, G1 belongs to W, and the G1 comma W belongs to G. So G1, it is a W value is G1 there. Thus the neighborhood of n epsilon Z subset of Z1, subset of equal to Z1. So Z is an interior point of G1. So therefore each Z belongs to G1. So G1 is an open, it's open. So let we can take that Z belongs to Z2 also taken here. Again, there is a delta greater than 0, such that W belongs to G whenever whenever we are taking W minus Z less than delta, W minus less than delta, if Z0 is polygonally connected to them. Z0 is polygonally connected to the W. So in the form of the argument, so Z comma W we are writing here, Z comma W subset of G. So the Z0 is already told what the polygonally. The end of the points we can take here. So the contradiction W not equal to Z1, W does not belongs to G1, must be in G2. Why? Because G2 is also open. The condition should be satisfied here. The theorem. Let the G be a connected open set. Then G is polygonally connected. Then G is polygonally connected. So let Z not be the point. Z not be a point of G. Let Z not be a point of G we are taking here. But we are defined, we have given and G2 here, we have given the one G is equal, we know that G is equal to G1 union G2, earlier we know that. So also we know that G1 intersection G2 not equal to. But G1 and G2 are non-empty, or not, there are open sets. So I yesterday earlier theorem also let they learn. But Z not belongs to G1, so therefore Z not belongs to Z not belongs to G1. So that G1 not equal to 5 of earlier theorem. So therefore G1 is equal to not 5, then only G is connected. So G2 is equal to 5, G2 not equal to 5 also taken. G is equal to G1 at every point. G is polygonally connected to Z0. So since that both Z0 belongs to G, is polygonally connected here. Compactness. So in the compactness, what we are taking a definition, a function f is bounded, a function f is bounded, a function f is bounded on a set contained in the domain of F, the domain of F. So if the function F is bounded on set, there is a, we are taking here in the domain of F we are taking here. So therefore there is a AK, there is a AK greater than 0, such that F of Z we are taking here less than or equal to K for all Z belongs to X. For all Z belongs to X we are taking here. Said to be local bounded. Locally bounded means at the point here, locally bounded the point on S, there is a some k greater than b 0. Some k greater than 0 is the open disk B. We can take in here center B such that F of Z is not equal to K whenever Z belongs to D intersection. This we are taking here. One theorem of locally bounded we can learn here. One theorem we have to learn here. Theorem. Let F be a continuous at A on S, so the F is locally bounded at A on S. So then F is locally bounded at A on S here. I'm taking one plus one. This is one definition on the F is also that one here. What's the differentiation? Now we have to learn the differentiation. The definition. You know. So before the theorem, I want to create the differentiation. Differentiation. The differentiation in the second. So what is the function? If we say the function if is said to be differentiable, if is differentiable at on interior point, at on interior point Z0 of its domain if limit Z tends to Z0 of Z minus F of Z0 minus Z minus Z0. So a function of specifically differential the interior point. So domain of that. So therefore we can take Z2 Z0 F of Z minus F of Z0 by Z minus Z0 also it can exist. So what but when F is differentiable here, when F is differentiable here, we are taking here A differentiable at A here we are taking here limit Z stands to Z0. So we can take F of Z minus F of Z0 by Z minus Z0 is called the derivative of the F at Z0 and it is denoted the first derivative means F dash Z0 of the first derivative we are writing here. So the function F dash the function we are taking here F dash that means Z stands to F dash Z. Z stands to F dash Z we are taking here whose domain is the set of points, whose domain is the set of points which F is differentiable is called as derived function of the derivative of F. I means domain means the set is the set of the points already. F is differentiable, that is F dash need not be writing here. So therefore the derived function here of the derivative of F. Therefore we writing F dash is not here. So therefore it is F dash is also differentiable, is not F dash also F dash also the first derivative again that called as F double dash Z naught F double dash Z naught. We can write this one F of F square Z naught or this is F double dash is also called the second derivative. The third derivative of the triple dash Z naught or F cube Z naught also we can use the derivation of it. This is called the differentiation. Use the notation F power n. So F power n means that is the derivative first, second, third, or anything you can write F power n of the nth derivative of it. You can write it here. But even though you can easily say that the function is differentiable Z naught understood Z naught is integer point. domain of it. So you can take here, define the derivative equally well by limit h tends to 0. Limit h tends to 0, we are taking a f of z naught plus h minus f of z naught by h, we are taking here several alternative missions are using differentiation. But two most popular being here df of z also we are using here, that is d by dz of f of z. That's the first derivative. You can write d by dz, d of f of z anna, d by dz of f of z anna, f dash z anna. All these are the first derivative functions. D square f of z is third, second, dq f of z, that is third one. D by dz of f dash z, the first derivative. D by dz of f dash double dash z, the second derivative. Again derivative for third derivative. What is the value of this one? So an example, so we have to learn here. See here. An example we have see here. So this is example what means let f of z here. One minute. See here, let f of z is equal to, let f of z is equal to z square, I'm taking here, and c taken here as the domain, c taken here as the domain of c is that the domain of f we are taking here. Let z naught. So what is the z naught here? Be any point of c, be any point of c we are taking. So therefore limit of, we are taking a limit of z stands to z naught with z f of z minus f of z naught by z minus z naught. So f of z minus f of z naught, z minus z naught here. So therefore we are taking a limit of z stands to z naught, z square minus z naught whole square by z minus z naught. So I'm taking the square part of here, therefore limit of z minus z stands to z naught. So that we are writing z minus z naught and z minus z naught. So we are writing here z minus the whole square. So z minus z naught cancel here. So what 2 z naught. So we are simplifying here. So we are simplifying the z minus z naught. So therefore 2 z naught we can simplify the z plus z naught is equal. We are writing here limit of z minus z naught, z plus z naught is equal to 2z naught for the above simplification. So therefore, if that z naught is equal to derivative, we are derivating this above function. So f dash is equal to 2z naught, right? Z square is a constant value. So therefore, 2z naught and z belongs to c. So again, derivative, this is a constant. Again, derivative, this one z naught will be removed here. Therefore, f double dash z naught is equal to 2. F triple dash is equal to, this is a constant. This is a 0. So therefore, does the n greater than or equal to 3 we are writing here. The first one, z plus z naught is equal to, first is the constant is 0, then 2z naught, then again one we are keeping the same here. So this is the values of f double dash 2, f double dash 0 also we can take simplification of the normal derivation. Then another theorem. F is differentiable. Z naught is continuous. Z naught. So if it is differentiable at z naught, then it is continuous at z naught. So therefore, limit which stands to z naught, we are taking here f of z minus f of z naught, we are taking here the limit which stands to z naught. So what is I'm simplifying the f of z minus f of z naught by z minus z naught, we are taking here. Therefore, z minus z naught, we are writing here. So therefore, f dash z naught. So therefore, the simplification of z minus z naught is cancelled. So first derivation is f dash z naught. So therefore, into 0 is equal to 0. So therefore, a limit z stands to z naught, f of z is equal to f of z naught also we are taking here. the most fundamental one. And also, not therefore f is continuous on Z naught, this one. So this is the very most important in our problems. So one problem to that we have to take that one in fourth problem. One problem. So that limit z stands to 1 to the power 4 minus 2 z cube plus 8 z squared minus 2 z plus 5 by z minus I is equal to 4 plus 4i. They are asking here, so therefore we can take that z is equal to not I. So we got idea what is the formula given here. Z power 4 minus 2z cube plus 8z square minus 2z plus 5 by z minus I. So in this one, we are taking see here 3z, z I am taking common here. So minus 2 minus 3i. So z naught is equal to I am simplifying here into z cube plus 5 minus 2i. I'm applying the values here, z plus 5i minus z minus I. I'm applying these values in the above equation. So therefore, 3z cube minus 2 minus 3i into z square, the one which will be removed here from the normal denominator part, 5 minus 2i to z plus 5i we are taking here. So, but which tends to 4 plus 4i by substituting the list type is continuous. C also we can take here also. And one other one we have to take we find the following limits. Limit z stands to 2 modulus of z also. So z stands to means is also tends means that is equal to tends also tends to means that is a 2. So limit z stands to 2 means z bar whole square is equal to what is z bar whole square is equal to 4. That's a simple one. And the limit z stands to 1 z square plus 1 by z minus z plus 1 z square plus 1 by z plus 1 we are taking here. Z square plus 1 by z plus 1 means so z square stands to what we have z square stands to plus 1 and that is z stands to is equal to plus 1 and z plus 1. So we are taking these values here. So therefore z plus 1 not equal to 0, therefore z is equal to 1. So therefore z square plus 1 by z square plus 1 means 2 by 2 is equal to 1. Why? Because we know that z plus 1 not equal to 0, therefore z is equal to 1. We are applying the same in this. So one that we have taken here. Examples you have to study this one. So many problems in the differentiation you have to study this one. Then analytic functions in the third year. You have to study analytic functions. What is analytic functions? What is analytic functions and harmonic functions we are taking here? So we have seen that earlier the set of complex numbers in unit 1. So therefore, the set of pairs of the real numbers are identical sets. So therefore, we review complex analysis, just a special case of the analysis function r square to r square. R square to r square, we are taking a distant with the defined r square. We shall need to use partial differentiation also. We can the Cauchy-Riemann equation. The Cauchy-Riemann equations. The Cauchy-Riemann equations here. So when we prove that z stands to z bar. So z is not a differentiable, but we did by computing here z plus h bar minus z bar by h. So when h is real and imaginary. We should real and imaginary parts. We know that h is a real and I is imaginary parts. So taking here, we get the values of the source here z plus h bar minus z bar by h is cannot have a limit. H approaches here is 0 here. Limit h up to 0. That is a technique followed in order to obtain some here necessary and sufficient conditions for the differentiability of the complex value function. So freedom we have to learn here today. The most important decision I would like to hear. If the function that is differentiable, if the function f is differentiable at the point, that z naught is equal to x naught plus I naught, real and imaginary part we are taking here. And f of x plus iy is equal to v of x comma y plus I into v of x comma y. So we are taking v of x comma y into v of x comma y. When u and v are the real and imaginary parts, we are taking here imaginary parts of it. So where u and v, where u and v, the real and imaginary parts, the real and imaginary parts of v. So real value function of two real variables, then u and v are partial derivatives. It's not going to satisfy the equation. So in this problem, we have to show dou u by dou x, x naught comma y naught, dou v by dou y, x naught y naught, dou v by dou x, x naught y naught, dou u by dou y, x naught y naught. So in the dou u by dou x, x naught y naught is equal to dou v by dou x. Dou v by dou x is equal to dou u by dou y, x naught y naught we are writing it. And also we are writing here f dash of z naught, dou u by dou x, x naught of y naught, the sign into dou v by dou x, x naught is y naught. Dou u by dou y, dou u by dou x, x naught y naught, and dou v by dou x, x naught y naught. So therefore, it's equal to also we have to dou v by dou y, the x value here we have x naught y naught, minus I into dou u by dou y. So here, see here, this is a x means we have plus and I mean y means this is y we are taking it and f dash z not we are proving here. So since f is differentiable, we know that since f is differentiable, it z not, since f is differentiable at z not, given epsilon greater than 0, there exists delta greater than 0. There exists delta greater than 0. F of z naught plus h minus f of z naught. Already I told f of z naught plus h minus f of z naught. H minus of the base minus of f dash z naught. So this is the less than epsilon, right? Because f of z naught is plus minus f dot by h minus f dash 0 less than epsilon. This is the condition what we are taking here. Whenever we are taking here, whenever 0 modulus of h less than delta, we are taking. So it is real. It is real and 0 less than modulus h less than delta. F of z naught plus h, f of z naught by h. F of z naught plus h minus f of z naught. So therefore, f dash z naught. Already put this is selected in the here this one. F of z naught plus h minus f of z naught by h minus f naught f dash z less than epsilon we are taking here. So, but the condition, what is the condition you have to write here? What is the condition here? F of z naught plus h, f of z naught by h we are taking here. Minus of is equal to, what is the condition u of? Real part I am taking here, u of x naught plus h y naught, u of x naught y naught. See here, very most important is the real part and the imaginary part. X naught plus h y naught minus V naught epsilon y naught. See the same values here writing, but real part and imaginary part and they separate here. Real part and imaginary part and separate here. So since the what is the real part and what is the imaginary part? See here, since real of this written on equal to yes, what is here, and imaginary part of this is not equal to this, we are taking here. A new complex number is we show you how that you have your x naught plus h and the same x naught is to y minus u of x naught is y h that is the dash of z that is then v of x naught plus h and y naught v of x naught comma y naught. This is the imaginary part what I am giving you. This is the real part, this is the imaginary part, and then both are less than epsilon. But whenever 0 less than minus of h less than delta the condition as but what we are taking here u of x naught plus u of x naught plus h y naught minus u of x naught y naught plus if it is imaginary part also we are writing u of x naught plus h y comma y naught minus v of x naught y naught by h. Both the values are we are writing, but even though these conditions are we have to prove here. First we are taking here dou u by dou x x naught comma y naught that is the real dash real applied signal and dou a by dou x x naught comma y naught is equal to imaginary dash signal real applied signal and imaginary applied signal. So on the other hand which is imaginary, on the other hand which is imaginary that is I into beta. Imagine that what we are getting I into beta. So therefore, where we are taking here beta is here, 0 less than beta are equivalently let 0 less than or modulus of beta less than beta. So we are taking the h is equal to I beta. So h is equal to I beta means 0 less than modulus of beta less than delta. So therefore, f of z naught plus I beta then f of z naught and making here that is I beta in the denominator of the result. So therefore, minus of f dash z naught so that is less than epsilon that is the condition of less than epsilon. But even though you have to write still here f of z naught plus I beta f of z naught by I beta that is v of x naught comma y naught plus beta v of x naught comma y naught. So what is here in place of beta I beta is equal real part and imaginary part I am separating here. Again I am separating the imaginary part here with the beta. Because with the beta imaginary part I am separating here. That is v of x naught comma y naught plus beta minus v of x naught comma y naught that is beta and beta. So therefore, this implies that here this implies that here v of x naught comma y naught plus beta minus v of x naught comma y naught that beta we are taking in. That is the real of f dash. The first derivation I am taking. The first derivation I am taking here v of x naught of y naught. So that is this is also less than epsilon. This is also less than of the epsilon condition taking. Therefore, minus v of x naught y naught plus beta. That is both are taking beta beta by beta is a minus image of imaginary of clarity. This is a real part, this is the imaginary part that is also less than equal to 0 less than beta less than delta. So wherever these conditions are, we are taking here. Wherever these conditions are, we are taking here. Dou v by dou y is x naught y naught. So from above the condition we are taking, that is the real part of the dash z naught dou u by dou y taking here x naught y naught. It is a negative. Why? Because I is taking the negative part from the above equation minus I minus imaginary part of that zero. So that means so both are minus here. So therefore the clear function is Rho u by dou x x naught is equal to rho v by dou y x naught y naught. So u actually dou u by dou x, dou u by dou y both are same, but dou u by dou x is not equal to minus here. U is minus, that is x naught y naught. So this is the above function. We are telling that this is the equation, is the Cauchy-Riemann integration equation. Even the real and imaginary parts of the Cauchy, imaginary parts of the function at the Cauchy-Riemann equation should not be differentiable to the point. However, with the extra condition, the function will be differentiable. Before proving, we are in. Then another one here, we have to learn here. It's a complex. A complex value. A complex or a complex value function. It is differentiable. It is differentiable. If a then there is a complex function. Then there is a complex function such that the form z is equal to the form here is a dash u with z minus a into plus phi r. See here, the target is z dash a z minus a plus phi r z. So what we have the complex function phi that we are taking here, but even though limit with z stands to a, phi of z by z minus a is equal to 0. Is a conversely, it is a complex number and this is a complex function phi such that f of z is equal to f of a plus x into z minus. So we are writing here this function f of z is z minus a plus phi of z we are writing here. So therefore, where the limit z stands to a, phi of z plus z minus z of z minus a. So then f is differentiable with a, then dash a is equal to. Yes, we are writing. What is the proof this one? The proof then f is differential. It is differential with a. We may define. We define here. We may define this one phi by phi of z. So phi by phi of z is equal. What we are writing in the earlier function equation f of z minus f of a minus f dash a into z minus a. So therefore f of z f of f dash a z minus a. So therefore the limit of x tends to a phi of z by z minus a. So limit of z stands to a, we are writing here f of z minus f of a by z minus a. F of z minus f of a by z minus a. But even though the first derivation of the f dash a is equal to 0. The first derivation of f dash a, you can take that the value is 0 automatically. Why? Because f of z minus f of z minus z minus z by z minus z not also the value of 0. So conversely, we are taking here also conversely z stands to 0. Phi of z by z minus a is equal to also 0. So phi of z is equal to f of z minus f of a minus into s minus z minus s minus z minus a is equal to 0 also we are writing. So therefore then we are taking here the limit z stands to a f of z minus f of a by z minus a limit z stands to a. So this f of z minus f of a by z minus a, we are writing here this is phi of z by z minus a plus s is equal to total value is equal to 0. So 0 plus s is equal to s what we have taken here. So hence f is differentiable, a and f dash a is equal to s. So f is differentiable, a and f dash a is equal to because we are writing here. We are learning here. Suppose I'm here. suppose f is equal to u plus I, where the function, where the function reference to an imaginary f is equal to b, now partial derivatives, now partial derivatives, now partial derivatives which are continuous, which are continuous, we are taking here at x naught comma y naught, we are taking here, and satisfy the Cauchy-Riemann equation with the and satisfies the what is the equivalent. So then f is differentiable at f is differentiable at f is differentiable f is differentiable at z naught is equal to x naught plus I y naught linear taking. So therefore, it is a derivative means f dash of z naught here, rho u by rho x naught comma y naught we are taking here, plus I into rho v by rho x naught of y naught here, rho v by rho x naught by, that is one function, and another one dou v by dou y x naught of y naught, again a clear one, what is minus r dou v by dou u by dou y, dou u by dou y x naught of y. See here dou u by dou x, dou v by both are plus, dou v by dou y, dou v by dou u by, first v is negative plus and v is negative, but we have taken as per logic to here. So this is the since u and v we are taking here, since u and v we are taking here, the partial derivatives of the continuous at the of the partial derivatives which are continuous x naught comma y naught. So therefore they are differentiable here. What's the differentiable here? How it is differentiable? You have to think here. X naught plus h and y naught plus k. That is u of x naught plus y naught. Then which into we are writing dou u by dou x x naught r. So I'm simplifying here and taking the imaginary part and taking here dou u by dou y x naught r prime. Again, constant also is there, that is rho into h comma. So what is the x naught? First imaginary part I am taking, then h taking, a taking, h is dou u by dou x and k into h into dou u by dou x x naught by naught. Now h I am taking, the common dou u by x x naught by naught. The k is taking common dou u by dou x naught by naught. Then in a constant function rho h comma. Then again we are taking the same of b here, b of x naught plus h comma y naught plus k, b of x naught comma y naught plus h into dou v by dou x. So I'm taking here x naught. This is dou v, this is dou u. So it is a v, and we are taking here v. So that's what we are writing here v, dou v by dou x of x naught y naught plus k into dou v by dou y x naught comma y naught plus sigma of h comma k. So sigma, both are using the different values here. What we are taking here, where we are taking here, limit h comma k tends to 0, 0, h comma k by under root of x square plus k square, limit of h comma k, that is stands to 0, 0, that is sigma of h comma k by under root of x square plus k square is equal to 0. This is equation number 1 I am taking. So rho of h comma k under the x square plus k square, sigma under root of h comma k under the x square plus k square. But what we are taking here, x is equal to h plus I k we are taking here. So therefore f of sigma plus what we are taking here, k you know that u of x naught plus h and comma y naught plus k, u naught plus k, then again that imaginary part, I into v x naught plus h, comma y naught k. So x naught plus h, there is a real and imaginary parts I'm taking here. U of x naught comma y naught I'm separating here. I into x naught comma y naught I'm taking here. H comma I'm removing h comma k, but I'm writing here the real and imaginary parts after writing here. Then h I'm writing here h dou u by dou x of x naught of y naught plus I into dou v by dou x naught of y naught. Then k, into dou by dou y into x naught of y naught plus I into dou v by dou y. So I'm writing u here, v by v here, so that is not plus compulsory v and u is minus, but it is I'm writing here v and the v. For the functions I'm taking the values here. So from the functions I'm taking the these values here. So therefore, rho h plus k I'm writing here. Plus k I'm writing right. Actually, to do x and x and y naught. I to do by the x and y naught I'm taking here. So this is the now we can this one here also we are taking here. Of course, z naught also taking here. So that is no before that another one. Plus rho of h comma k plus I into sigma h comma k. All the values we are taking, all the values we are taking here. So therefore, since when we so therefore this transaction since when we satisfies Cauchy-Riemann equation, since when we Cauchy-Riemann equations here. So therefore dou u by dou y x naught comma y naught is I into dou v by dou y x naught comma y naught minus of dou v by dou x x naught comma y naught plus I into dou u by dou x h naught comma y. This is a real part and imaginary part is mandatory minus here. So therefore we can write here I into dou u by dou x of x naught y naught plus dou v by dou x naught y naught also we have to write here the imaginary part of the taking the front in the condition. So therefore also we are taking here also the part z naught is equal to u of x naught comma y naught plus I into v of x naught comma y naught here again. Therefore, sin dou u by dou x x naught y naught plus I into dou v by dou x x naught y naught also we are taking here. So now we can write this f of z naught plus h. We are writing here f of z naught plus h plus I rho of h comma k plus I into sigma h comma k. The values have been I'm writing here. Apart from these values here, you can write here, you can write the values here. This is a simplification of this value here. This one into pi of s you can write here. So we have written pi of s equal to rho of h comma k. Pi of s is equal to rho h comma k we are writing here plus I into sigma h comma k we are writing. Therefore, we are taking here pi of s h comma k plus I into sigma h comma k by s we are taking here less than or equal to rho h comma k by s. Yes, also I'm taking here plus sigma of h comma k. Right. So what is the values I'm taking here? What is the implication of the values I'm taking here? And applying the same here for the modification here. Rho of h comma k by under root of h square plus k square. That means is we are taking here plus minus of h comma k. square square is equal to stands to 0. So therefore, here in the first equation, what is the first equation? What we are told f of h comma k, that is k stands to 0, 0. We are told here that at that point. So therefore, the f is differentiable. So therefore, f is differentiable. We know that. So therefore, dou u by dou x, x naught of y naught is equal to dou u by dou x naught of dou u by dou y x naught of y naught is equal to dou u by dou y x naught y naught. So dou u by dou y, dou u v, so v u means 5. So the condition is satisfied here. So it is a reliable of the function that f is differentiable. Z naught is equal to x naught plus I line of the condition. It is differentiable. Then one example, one problem we have to learn here. Suppose one of the most obvious and useful consequences of that this theorem, two new technique finding the finding whether model section find a function differentiable and derivative it is differentiable. If the derivative is differentiable, what we are doing here, then that problem we have to learn here. F of z is equal to z square. Z is equal to x plus I. F of z is equal to what we have to write, x plus I, right? Z square means x plus I whole square. What is the form? A plus b whole square, x square minus y square plus y square. I square means minus 1 plus again minus 1 2y x y. This is a basic fundamental formula u of x y. What's the real part here? X square minus y square. In v of x, what here we have imaginary part? I we have to do. So the partial derivative what we are taking here. Partial derivatives are dou x, x comma y. That is partial derivative is only x and this is y, that is 2x. Dou u by dou y, 2xy to xy, x comma y is equal to that is minus 2y. Why? Because this is 0, this is minus, minus 2. And then dou u by x of x comma y. Again 2y, dou u by dou x, that dou u by dou y comma y is equal to 2x. This is the fundamental value for this one. This is a differential function here. So another one, f of z is equal to modulus of z of z. Of z is equal to modulus of z. F of z is real or always, therefore g of x comma y is equal to 0. And u of x comma y, u of x comma y is equal to under root of x squared plus y squared. Now the partial derivatives of u do not exist in the region, so f is not differentiable here. So therefore x comma y not equal to 0, 0. So x comma y not equal to 0, 0, what we have to do? Dou u by x equal to x comma y. That is x by delta x square plus y square. Then dou u by dou y x comma y is equal. That is y. Here x is there, x here y is there, that y by the root of x square plus y square. So dou v by dou x is equal to x comma y here. Dou v by dou y x comma y. So b below x and below y, both values are equal. Partial equations are not satisfied. Why? Because f is differentially out here. So the partial equations are important theoretical consequences also here we are stating here. Now another function which is differentiable at every point. The function which is differentiable at every point of the region R said to be analytic. Function analytic on C is said to be function an analytic function, analytic of complex numbers is said to be an intent. So it's mainly with analytic functions which are deal with the analytic functions only. But definition we have to study here. Any polynomial function is entire. Also, any rational function P by Q. So where P theorem also you can take P theorem. Function is entire. Also, the rational function P. So where P and Q, where P and Q are polynomial functions is analytical reason. Analytical reason we are taking an analytical region that belongs to C. Q of Z not equal to 0. So, but the Z belongs to set Q not at C means it's a complex number. The C Z value is there, but Q of Z not equal. Q of Z is equal to 0, there is nothing. Zero something. So the product rule is inductively shows that the function Z stands to Z power n is entire and has derivative Z stands to n into Z power n minus 1 everything. The polynomial is sum of products of functional constant functions. Yield is therefore differential is everywhere. By the second rule, the rational function is differentiable everywhere, which is denominator of the rational function is not. Not zero is the only denominator of the rational function, only the condition should be satisfied here. Okay. This analyze the confusion. Dash z is equal to 0. Wrong set in R then the is constant. It is constant or not. So we have to first we have to show that the given the point is Z naught in R. So there is a disk with the center. There is a disk with the center. There is a disk with the center. Z naught contained in R we have to here. But which F is constant. But let we have taken here. Z naught belongs to R. Since R is open. Since R is open we are taking here. So there is an open disk D center. There is open disk D center Z naught contain R. So therefore here, so therefore Z naught contained in R, f of x plus I by we are taking here by dx of x y plus I into rho v by dx. We know that already I told you rho v by dx x y and I used to see here what we are taking here. So dou u by dx x comma y plus sin into dou u by dx x comma y. Again we know that here I into so dou v by dou x of x comma y minus I into dou u by dou x of x comma y. So is the value is 0 for all real and imaginary part x plus I y, x plus I y in R we are taking here. So therefore, again, so therefore x plus I y is equal to x plus I y in R we are taking here. And also here, rho u by rho x and rho u by rho x, x comma y, and the rho u by rho minus x comma y. Again, we have to rho v by rho x and x comma y is equal to rho u by rho v by rho y. This is rho v by x, this is rho v by rho y. X comma y, all values are 0 here. What we are taking here, so therefore, since we are taking here, we are writing here, since we are taking here rho u by rho x, x comma y naught, rho v by rho x, x comma y naught, we are taking rho u by rho x, rho x by x comma y naught, we are taking 0 functions. So the 0 functions we are taking here extends to u x naught from x comma y naught, but extends to u x naught x to y naught we are taking here. So what is extends to y naught and why we are taking here? So I have right here z1 is equal to x1 plus I1. Z1 is equal to x1 plus I1 is any point in B. Then we are writing here the of x1 plus I by y. x1 plus I by naught is equal to the right. This is x, so real part is x1 minus part of writing here u x1 comma y plus I into b x1 comma y is equal. So therefore u of x naught comma y naught plus I into b x naught comma y naught. So this is not, this is not here. So therefore f of x naught plus I and y naught here taking this condition as true. Again here, again, since rho u by rho y, x1 comma y we are taking here, rho u by rho y, x1 y we are taking is also 0, and y stands to u of x1 y. So therefore y stands to u of x1 y, or y stands to u of x1 y also constants here. So the condition of f of x1 plus I by 1 I am taking here u of x1 comma y1 plus I of b x1 comma y. So really my thought u of x1 comma y0 I'm taking here. Here also I want to be x1 comma y0 I'm taking here. So now I'm getting f of x1 plus I by 0 f of x0 plus I naught. So we are doing imagine the part I'm plugging here. X1 plus I naught also can be there. X0 plus I by naught. So therefore, what we have taken here f of zi, f of zi is equal to f of z naught. We are writing the once it is constant and is to be let g1 is equal to z belongs to R. F of z is equal to f of z naught. And z2 is equal to also we are writing here z belongs to R. So f of z not equal to f of z. So f of z is equal to f of z naught, f of z naught equal to f of z naught. What the z belongs to R, that is g1 and g2. Separately we are taking here from the we know that g1 not equal to phi also. We know that. So there is exists a d simple z naught. So therefore f of z is equal to f of z. So f of z is equal to f of z naught for all z belongs to g. So therefore g2 also not equal to phi, we know that. And see that the set is equal to H is equal to W belongs to C, W belongs W naught F of Z naught. So then the set is then the set H set is open, when the set of H is open. So further F inverse H, that is pre-image of the set, under F inverse G is G2, under F inverse is G2 here. So since F is continuous, F inverse is open, so G2 is also open condition. Now we can do that G1 is also open, G1 belongs to G1. There exists an open disk decenter G1 contained R. F of Z is equal to G1 for all Z belongs to G. So G1 is open. So G1 is open, not we have anything. G1 is union G2. So G intersection G2 is equal to 5. So our non-empty open says the disconnected which is contradiction G2 not equal to 5. So that's open becomes all the if F is analytic and check R and one of the following conditions is real part is constant R imaginary is constant modulus then is constant make is constant. So this is the freedom principle, fundamental freedom. We know that the first we have to prove 1, 2, 3 conditions here. We write here, proof here, writing here, we write here. If is equal to replace IV. Assume that U is a constant amount, U is a constant amount, dou U by dou X is X, comma Y is equal to here. Dou U by dou Y is equal to. You know that for all X and Y, for all X and Y, such that X plus Y, X and Y, such that we express IY, express IY express IY is in all. But F dash we are taking here. The first representation of dash is X plus IY is equal to dou by dou X comma Y, we are taking I into dou by dou X, that is X comma Y. Then again we are taking dou U by dou X, dou U by dou X comma Y minus I into dou V by dou Y X comma. So dou V by dou X, dou V by dou X, dou V by dou X, so with Y here, so therefore we are negative minus we are writing here. So therefore dou V by dou X, dou U by dou X comma Y minus dou V by dou X comma Y. So the condition should be satisfied, the Cauchy Riemann equations are satisfied. We have that F dash is equal to 0 on R. And so second also we also the same. We also the different similarly we are taking the third condition of physical U plus IV dash B therefore square plus V square is constant and R. Constant and R. And so the partial derivative of the partial derivative of V square plus V square R 0. V square plus V square R 0. So therefore plus IY belongs to X plus IY belongs to R also. Therefore U of X comma Y dou by dou X comma Y U of X comma Y dou by dou X Y is equal to 0. Then U of X comma Y dou U by dou Y X comma Y plus U of X comma Y dou U by dou Y X comma is equal to these functions are here. Using Cauchy Riemann equations, you can write here comma y. Over x comma y equal this sum. U of x comma y. Yeah, x comma y. Over x comma y. Okay, this is a very variable and variable the real and imaginary part that is equal to 0. So therefore, u of xy, dou u by dou y xy, and again this is again negative dou u by dou y writing the same value. V of xy dou u by dou x is the mandatory plus x comma y. So again both on your solving here, both on this is u of xy whole square plus v of xy whole square. You can write it. Then into dou u by dou x comma y is equal to 0. The first thing. And the second one again squaring here, then v of xy x comma y whole square plus v of x comma y whole square. That is dou u by dou y. Then z y is equal to 0. But u square plus v square is constant height because the real part here is not. Therefore, square plus v square is constant height. So 1 0 dou u by dou x comma y is equal to y and x comma y. So it's equal to the part of therefore r. So there's square, there's u square plus v square is equal to 0. So u square plus v square is equal to 0. Therefore u is equal to 0 and v is equal to 0. And again, and there is again constant fundamental function. This is what tomorrow in the class we will discuss harmonic function. What is harmonic function? Two-dimensional Laplace functions here. This is the question today. Two Laplace function, that is those Laplace function rho square pi by rho x square plus rho square pi by rho s square is equal to 0. So this function phi of x comma y is a potential theory. Applications particular fluid elements closely connected to complex function f is equal to g plus iv. Analytic in illusion, u and v satisfy above partial definition. These are also satisfy partial modification, but the close continuity of partial derivative also v. So find that analytic function the region differentiable in condition of the second partial derivative v. However, you can take the harmonic functions. So what is the definition of harmonic? Any function satisfying set to be harmonic function, potential function. That is what is the rho square pi by rho square. Right? So tomorrow we can discuss the harmonic function. Will you ever ask me